We already have a somewhat intuitive sense of how number systems work. And the idea revolves around how many fingers do we have? So as human beings, base 10 makes sense. But a computer, which receives either a high or a low signal, it would make sense for us to think about that system as having only 2 fingers, and therefore keeping track of multiples of 2. Hexadecimal is also a very common number system used in computer systems. And so one of the questions we may have is, how do we convert from a different base into base 10? And we need to be able to do this, especially if we're going to have a computer perform some sort of arithmetic for us. So the intuition behind this, we'll start off by thinking about a number that is, suppose, that's in base 2. So we're going to start off looking at something that's in binary. So we'll look at the number 110. We've already described these digits as representing the number of groupings of 2, or the number of individual, and the number of ones, which could be either 0 or a 1, the number of groupings of 2, which could be either a 0 or 1 grouping of 2, and then we have to look at the number of groupings of 4, and that could be either 0 or 1 groupings of 4. So the first digit tells us how many groupings of 1 we have. In this case, that's the same thing as saying 2 to the 0. Then the second rightmost digit, or the digit to the left of that, tells us how many groupings of 2 we have, and that could be 0 or 1. The digit to the left of that tells us how many groupings of 2 we have, or how many groupings of 4 we have in our value. And so if we now deconstruct this, we're saying that we have 0 groupings of 2 to the 0, plus we have 1 grouping of 2 to the 1, plus we have 1 grouping of 2 squared. And in this sense, we really see that we have 0 ones, if we're now thinking about this in terms of as an integer representation, plus we have 1 grouping of 2, and so 1 times 2 is 2. And then we have 1 grouping of 4, which is plus 4. And so this number equates to 6. So the binary 110 is equivalent to the integer 6 in base 10. And the way we could write this is to say 110, put parentheses around it, a subscript of 2 to indicate that set of values is in base 2. We can't not put that there. Just because we see 1s and 0s doesn't inherently mean that number is in base 2. This could be 110 in base 10, or it could be 110 in hexadecimal or octal numbering systems. So we put this little indicator on here to indicate that that's in base 2, and that is equal to the number 6 in base 10. Now in base 10 we oftentimes omit that, because if we write the number 6 we just assume that that's in base 10. So it's not really necessary for base 10 purposes to write this, but for consistency it would be a totally valid way of representing that. Now suppose we have something in hex. And let's say that we have the number A0B. Now in hexadecimal, we're counting in groups of 16. So the first value tells me how many individual tick marks I have. So in other words, how many 16 to the zeros I have, which is just saying how many 1s do I have. I could have 0 all the way up to 15. Once I get the 16th individual tick mark, now I have to iterate over to the left and say, okay, well now how many groupings of 16 to the first do I have? And I can have 0 all the way up to 15, right? So 15 times 16 is how many individual elements I could have in base 16. But then once I get to the 16th grouping of 16, now I'm talking in 16 squares. How many groupings of 16 do I have? All right. Well, in much the same way, we can deconstruct this and say that in this case we have B groupings of 16 to the 0, and we'll convert this in just a second. B groupings of 16 to the 0, plus I have 0 groupings of 16 to the first, plus I have a groupings of 16 squared. Now we have to convert these because b is not actually a numerical value that we can work with, but if we recall, a in hexadecimal is actually equal to 10, b is 11, c is 12, d is 13, e is 14, and f is 15. So that means that in this case I have 11 groupings of 16 to the 0. I have 0 groupings of 16 to the first. I have 10 groupings of 16 squared. So in other words, really what this means is that I have 11 ones, plus I have, 16 to the first is 16 times 0 is 0 groupings of 16, plus 16 squared, 16 squared is 256. 256 times 10 is 2,560. And so now I'm just working in standard base 10, and 11 plus 2,560 is 2,571. So the conclusion I can make is that A0B, which is in hexadecimal representation, is equal to 2,571 in base 10 representation, and if I want to omit that base, I can just say that that's equal to 2,571. So the beauty is that every single binary, hexadecimal, octal value can be represented in base 10 by thinking in terms of groupings of however many fingers we're talking about. Whether we're talking about having hands collectively having 2 fingers, hands collectively having 16 fingers, hands collectively having 8 fingers, etc. So to formalize this a little bit more, this theorem states that let b be an integer greater than 1. Then if n is a positive integer, it can be expressed uniquely in the form n equals, and you can kind of see already the structure of what's going on here. Now n is typically our base 10 value, and b is the base whatever we're working in. So I'll just call this base b. Okay, so let's say that what we want to do is to use this formula to convert the 110, which is in base 2, and we want to know what is this going to be in base 10. So the way we could represent this is, in this case, our b is 2. Our n is the value that we're trying to determine. Well, what we're going to do is we're going to say n is equal to a sub k, that's the number of groupings that we have. So in this case, this is going to be a sub 2 times b squared plus a sub 1 times b to the first plus a sub 0. Okay, so a sub 2 is right here. That's the 1. Here's a sub 1, and here's a sub 0. So those are just the individual digits of our base 2 representation. So we'll have a 1, and a 0 here. And now you could also write this as b to the 0 if you chose, b to the 0, but whatever that base is, raised to the 0 power is 1. All right, so our base in this case we said is 2, so this is 1 times 2 squared plus 1 times 2 to the first plus 0 times 2 to the 0, if I want to write it like that, or I could just leave it as plus 0. And you can see that that's exactly the same computation that we did up here. We just did it in reverse. We started from the rightmost and worked our way to the left. But the way this theorem is constructed is it starts with the leftmost digit in your base b representation and works all the way to the right. And so this still comes out to 4 plus 2 plus 0. So 4, 2, and 0 are now in base 10 representation. And this comes out to the integer value of 6. So now we know that this question mark, that is going to be 6 in base 10. We could do the same thing in our hexadecimal representation, which was the number A0B in base 16. And we want to know what is that number going to be in base 10. So following the same principle, we are in B equals 16. We see that we have 3 digits, so A2, A1, and A0. Notice our indexing goes from 0 all the way up to the number of digits minus 1. So we actually have 3 digits, but we only go up to A2. So the the base 10 representation will be A2 times B squared plus A1 times B to the first plus A0 times B0. B to the 0. Now, otherwise, our intuition is perfectly fine. There's nothing wrong with the way we've done this intuitively, but if we want to instruct a computer or write a piece of code that converts between number systems, the intuition is simply not good enough. It needs to be formalized in a way that a computer can actually carry out the task without having to somehow think intuitively and abstractly. So this formula will do it. So our A2 is A, and we said that A is just really the hexadecimal representation for 10. B in this case is 16, so 10 times 16 squared, plus 0 times 16 to the first, plus B, which is 11 times 16 to the 0, or really just 11. And so this is where we came up with our 2,560 plus 0 plus 11. And notice again that that's just the same thing we came up with here, just in descending instead of ascending order as we've done. So 11 plus 0 plus 2,560 comes out to 2,571. And so once again, this number here in base 10 is 2,571. Let's do one more quick example. Let's say that we're working in base 11. So maybe what we have is, or let's do base 8. So we'll say we have 7, 3, 6, and this number is in base 8. Again, if I just give you the number 736, you would assume that that's 7 100s, 3 10s, and 6 1s. But now we're saying that this is actually counting in base 8, so we'll only have 8 fingers. And once again, we could say that, well, we have 6 individual ticks, which is fine. We have 0 all the way up to 7 that we could utilize. Then we have 3 groupings of 8, and then we have 7 groupings of 64, right? Because once we get to that 7th grouping of 8, which is 56, then the 8th grouping of 8 is 64, which makes this digit the number of 64s that we have. So once again, we allocate this digit to be A2, A1, and A0. And now that we have this neat little algorithm where B is equal to 8, we know that the integer, or the decimal base 10, representation of 736 in base 8 will be A2 times 8 to the 2 plus 3 times 8 to the first plus 6 times 8 to the 0, which I'm just going to go ahead and omit that since that's just the number of individual ticks that we have. And so 8 squared is 64. 64 times 7 comes out to 448 plus 24 plus 6, which gives me 478. So that tells me that 736 in base 8 is equal to 478 in base 10. And once again, I could just say 478 because we assume we're in base 10. That's our default base, our number system. And we have this beautiful way of now converting from base B to base 10.